Choosing EMG signal. And our mentors are Professor Anshu ma'am and Vanshida sir. And our team is T. Ravindra and Raviteja. So coming to introduction of the project, EMG signal is a biomedical signal that measures electrical current generated in the muscles during their contraction. And quadriplegia is paralysis that affects all the four limbs. So such quadriplegic individual may require assistance to perform the tasks. So identifying the neck movement is the crucial part of identifying the type of action that we need to take. Then motivation. First thing is independence. So quadriplegic people often require assistance with everyday tasks, and a device like this will help them to regain their independence by allowing them to perform tasks on their own. And second thing is safety. Assistive device like this can help the people to avoid injuries. So for example, let's say a device like this can help them to move from wheelchair uh, to bed or a toilet, and it will reduce the risk of fail. Independence. So quadriplegic people, they'll often require assistance with everyday tasks, and a device like this will help them to regain their independence by allowing them to perform tasks on their own. And second thing is safety. Assistive device like this will help them to avoid injuries. So for example, let's say these devices will help them to move from wheelchair to bed or toilet, and it will reduce the risk of falls. And thirdly, to increase the productivity. So by using these devices, they can increase the productivity and participate more fully in the workforce. And the last thing is social inclusion. The project has significant social impact by promoting equality and inclusivity, and accessible to people with disabilities. And our solution for this challenge is to uh, firstly we'll extract the EMG signal from their body, and then we'll amplify it, which is necessary to increase the signal strength. Then we'll purify through the bandpass filter, which will remove the unwanted frequencies. So second step is to classify these purified EMG signal based on the intensity of the muscle movement, which is then translated into instrumentation for controlling the device. And finally, the whole process involves multiple steps like first thing is signal extraction, next purification, amplification, and then processing to enable the use of EMG signal. Then the project is divided into two steps, which is extraction and classification of the EMG signal. The first block diagram on the left explains the first step, which is extraction phase. So electrodes are placed on the neck region, which extracts the signal, and then signals are amplified using instrumentation amplifier, which are finally filtered out and which are finally filtered out using the bandpass filter. Then, then coming to the second part. So block diagram on the right side explains the classification part, and the signal extracted is fed to comparators to classify the movement based on the intensity by setting some threshold DC values, and then the signal is given to triple for timer, which sustains the short pulse generated by the comparators and makes the bulb go for 1 second at least. Then the combination logic ensures that only one of the bulb glows at a time. So coming to the this is the simulation part of the step. So first we need to feed the signal to our instrumentation amplifier, which has a gain of 400. Then it goes to filter, which limits the frequency of the signal between 20 Hz to 500 Hz. So here is the gain calculation of the instrumentation amplifier. So we have set the register values of the resistors in such a way that the entire gain of amplifier can be changed by just changing the value of Rg according to our convenience. So we fixed the R5 and remaining all other values. And the crucial part is that uh, why did we choose the instrumentation amplifier? So we also tried the differential amplifier that we have read in the first project, and we compared the CMRR values of both instrumentation amplifier and differential amplifier, and we found the CMRR for instrumentation amplifier to be more as compared to differential. So we choose the instrumentation amplifier. So here we can see the CMRR calculations, which I just explained now. Then these are the LT-Spice outputs of the amplifier. As you can see, we got amplification of 400. Then this is the hardware circuit output of the oscilloscope, which is perfectly giving the gain of 400. Then frequency above 500 Hz and all the frequency below 20 Hz. These are the cutoff calculations for high pass filter and low pass filter subparts, and we have also calculated roll off. And this is the LD-Spice outputs of the filter. Looking at the magnitude plotter for the band pass filter, the points where the magnitude is minus 3 dB of the maximum gain. So those points represent the cutoff frequency of the filter, and those are measured and those are found to be 20 Hz and 500 Hz for high pass and low pass parts. This is the hardware circuit and the output of oscilloscope. The plot of magnitude and phase are expected, and those are exactly matching with the spice simulations. This is the entire spice simulation for the first part, which is the extraction after amplification and filtering. These are the hardware of the same circuit and the oscilloscope output from uh, after filtering. So this is the practical signal that we got after extracting. So the image on the left shows the EMG with not moving, not having any movement in the neck, and the image on the right showing the EMG signal with the intermediate neck movement. So these are some more plots. The left signal is showing the intermediate movement, and the right image is showing the strong movement. So let's go into second step, which is classification. To classify the movement based on the maximum amplitude of the signal, we use comparators to check the signal crosses the peak of the comparator, which gives a sudden low to high pulse, and then which will trigger the triple timer. So the main purpose of the triple timer is to increase the duration of the bulb, as the signal generated will be only pulse, which is a short time. So to increase the time of the signal, then we are giving it to triple timer. So we use a combination logic to make sure that when a mg signal is value is more than a peak value, then both peak and intermediate comparators will glow. So to remove that, we are using combination circuit. So by connecting the triple timer in the monostable mode and adjusting the values by resistors and capacitors, we generated a pulse of 1 second, and this is used to trigger the LED. And this is the LT-SPICE simulation of the output of the triple timer. And this is distortion analysis. Basically, distortions will occur due to various factors as interference and noise and these all. This will affect the performance. So basically, it is the square root of sum of all amplitudes at the harmonic frequencies. So those are calculated, and these are LT-SPICE outputs of the distortion analysis. So finally, we can improve our project by adding some sensors, which is integrating with IoT, and which will help us by adding more sensors to the system. It will help detect more movements. And second thing is increasing accuracy. So cascading circuit with the Arduino will increase the accuracy for post processing part. And we can make it wireless by connecting to ESP32, and can make more convenient to use and allow for better mobility. We can also incorporate machine learning technique to improve the classification accuracy of the system and provide better control of the movement. And customization, so we can improve the device usability. So rather than having detecting only the neck movement, we can also detect the muscle movement based on person. So it depends on person to person. So the main challenges faced are, first thing is the choosing the right part, right area. So the electrodes is the first challenge. So we are given three electrodes, which is positive, negative, and reference. So the positive and negative electrodes has to be placed on the two ends of the same muscle to get the right spike, and the third reference electrode has to be placed from an area alienated from the muzzle under observation for it to act as reference. So all the signal amplitudes were obtained initially when kept near the neck, whereas the when we placed those on hand were more satisfactory than the signal we got when we kept on neck. So since our project is for quadraplegic individual, we carefully calculated the right amount of amplitude gain for the neck signal. Uh, and the second main problem we faced is deciding threshold values for bracketing, uh, classifying strong and weak muscle movement. Basically, it is subjective and varies from person to person, and even it varies for instance to instance. So even for the same person, but we still have to come up with some suitable values. So we came up after long experimentation. And another issue was to implement this distinction on hardware level. And after some research, we thought compared with proper DC value as reference would output 1 when the input signal is greater, and 0 otherwise. Another major issue was the fact that the spike will exist for a instance only. So when we directly connected the output to comparators output from compared to LEDs, they were very rapidly flickering continuously due to the signal. So we want a delay circuit with which could sustain momentary signals, and for this we made use of the preferred timers, which when triggered gave pulses of required time for in the formula 1.1 RC, thereby ensuring that flickering it doesn't happen. Once again, the issue with the signal had if the amplitude of the signal is greater than both threshold, then both of the LEDs will be switched on. So we have to use a combination logic to ensure that only one of the LED glows at a point of time. And we also, as we are using triple for timer, it needs a negative edge to be triggered. So we use another NOT gate right in front of the input of the triple for timer. After that, the signal is generated. So finally, in conclusion, so this will help the individual with quadriplegia to control electronic device. So we successfully designed and implemented, which will extract, filter, and amplify, classify the signal to control the device based on the movement of the muscle. So throughout the project, we demonstrated the use of EMG signal to assist the quadriplegic person. This will enhance the quality of life of individual with quadriplegia. So furthermore improvements can be made to increase the accuracy of the instruction that the person will give and reliability of the system. And we hope our project will inspire for future developments in this field. So thank you.